Okay, let's continue. So, a torque is a measure of how effectively a force causes rotation. Which force A or B, will cause the greatest rotation? Okay. And we talked about this a little bit already, but I want you to think about when you push open a door. Okay, so let's say that this is the hinge of the door, okay, and you go to push it open. You instinctively will not push close to the hinge. You will push further away because you can get more rotation. Okay, so like you're not going to push close to the hinges. You're going to push further away because it's easier to rotate the door when you do that. And it's something I want you to try. I want you to, the next time you're pushing a door open, I want you to first realize that you're pushing further away from the hinges versus closer to the hinges. And then the second thing, I want you to try pushing closer to the hinges and see how much harder it is to cause that door to rotate. It's actually really interesting, the difference there and how we do this without even realizing. But the concept behind it is torque. Okay? And so which force is going to cause the greatest rotation? Well, that'll be force B, because it's furthest away from that point of rotation, right? That axis that we're going to be rotating around. Identify the lever arm in each case, okay? So for force A, our lever arm is from that point of rotation where we're rotating around to the force that's being applied, okay? So the lever arm would be right there. But if it was force B that we're talking about, then the lever arm is there. Oh, yes, these equations. So this is the equation for torque, okay? There are these two equations, and there's actually a third equation, which is kind of a combination of the two that I think actually works the best. I think conceptually it makes sense. And so we're going to write this off to the side, and I bet you'll find that you'll be using that equation more often than the other. And it's just torque, that tau, is equal to force perpendicular, okay? The perpendicular component of the force, and that's what that little symbol means. Force perpendicular, and then multiplied by r, where r meaning radius, like radius of a circle. And so if like here we're making this circle with the force, then the radius would be there. So a good way of looking at this is r is that lever arm. Okay, it's that distance from point of rotation to the force that's being applied. Okay? So I like this perpendicular component of the force versus that distance, and we'll talk about this sine. And so we took the r component there and sine theta. So let's talk about that. We have a similar situation. Like let's say we have a wrench, okay, and let me draw that. And we're trying to turn a bolt. Okay, so we're trying to turn a bolt, and we're going to pull or push on this wrench, but we're not going to push on it perpendicular or parallel. It's going to be at an angle. Okay, so we have some force that we're going to apply. Okay, some force that we're going to apply to this wrench. Okay? Now, there's two components to this force, right? There's that X and Y component. We can also call it perpendicular or parallel, and to our lever hand here. Okay? And so we would have force perpendicular, right? It makes a right angle with that lever arm. Or we could have force parallel, right? This component of the force is parallel to the lever arm. Okay? And we'll have some theta, right? Some theta that tells us that angular displacement. Okay? So, what is force parallel? Sorry, perpendicular then. Like if I know the amount of force I'm pushing and I know the angle that I'm pushing at, how can I solve for this? Okay. Well, we know that sine of theta is equal to opposite over hypotenuse. And so then if we rearrange that like we've done over and over again at the first half of this class, we would see that force perpendicular is equal to the whole component of the force, sine theta. So that's kind of where the sine theta component comes in. It's right there. And so we could rearrange this equation since we know that the perpendicular force is a force multiplied by sine theta. Here's what you need to be really careful about. If we're talking about a different theta, and you'll see this in example number 1. If we're not talking about the angle from the lever arm, then it may not be sine. Okay, may or may not be sine. And so what I really like, I like leaving it as this, just realizing it's the perpendicular component of this force. It's not going to be the parallel component of this force, because if I push on the lever arm with a parallel force, it doesn't rotate. But if I push on it with a perpendicular force, then it rotates. Okay, so it's only the perpendicular component that's going to cause that rotation. And then the distance is the other part of that. So if my force doesn't increase, my force stays the same, right? Just like up here, the length of these arrows, the magnitude of the force, they're identical. But one has greater torque, and that's because the lever arm is greater. That distance away from the point of rotation is greater. R is bigger for force B, for torque B, and so it's a larger torque than torque A would be. Okay. Example problem number 1. A bolt on a car engine needs to be tightened with a torque of 35 Newton meters. You use a 25 centimeter long wrench and pull on the end of the wrench at an angle of 60 degrees from the perpendicular. Okay. It's really important to recognize which theta we're talking about there. How long is the lever arm, and how much force must you exert? Let's draw a picture of what's happening here. Okay. A bolt on a car engine tightened. We have a torque that we're applying, or needs to be tightened with that torque. You use a 25 centimeter long wrench to pull the end of the wrench at an angle of 60 degrees from perpendicular. Okay, so we have our wrench here, turning this bolt, and we are pulling on the end of the wrench. Okay, so let's just we are pulling with a force on this wrench here. And it's telling us that we're pulling at an angle of 60 degrees from perpendicular. So this would be parallel, right? Here's my lever arm, so that would be parallel, right? And so if I do this theta, that would be from parallel. But it didn't say that, it said from perpendicular, and perpendicular to this lever arm is right there. And so if I'm 60 degrees from perpendicular, that means that's the theta that we're talking about. Okay? And this force, again, it can be broken up into force perpendicular and force parallel. That this component of the force is parallel to the lever arm and that one's perpendicular. And you see now, because we've changed that this is theta from perpendicular instead of from parallel, that now our force parallel is no longer sine of theta for that angle. It's cosine because it's adjacent. Okay? Let's walk through that. We know from SOHCAHTOA, from our trig, SOHCAHTOA, that cosine of an angle will equal adjacent. Well, to this angle, what's not opposite from it, but adjacent to it, is that force perpendicular divided by the hypotenuse, which is the whole force component there. Okay? So if I want to know this parallel force, I'm going to multiply this perpendicular force, then I want to multiply both sides by the whole component of force, right? I'm going to multiply this side by force and that side by force. Ooh, don't want to get those mixed up. And so force cosine theta is equal to the perpendicular component in this situation. Okay? And it's asking us, first, how long is the lever arm? Well, we use a 25 centimeter long wrench. So this wrench is 25 centimeters, but we need it to be in meters. We didn't kind of address this. Units of torque is Newton meters. It's a force multiplied by a distance, right? A force multiplied by a distance. And so it's going to be in meters. So instead of 25 centimeters, it's going to be 0.25 meters. Okay? That's how long my lever arm is. 0.25 meters. How much force must you exert? Well, we know that torque is equal to force perpendicular times by that lever arm. And in this situation, that perpendicular component is force cosine theta. So this would be the same thing as torque is equal to force cosine the theta that they've given us multiplied by r. And we're solving for force. So we'll divide by cosine theta and we'll divide by r. So we have our torque divided by cosine theta and divided by r, and that will equal force. And I'll plug that in. Okay, so we know that torque from the reading needs to be 35 Newton meters. Okay, so I'm going to take 35 divided by cosine of 60. Let's add a decimal there, so we're working with 2 sig figs instead of 1. Multiplied by r, which is 0.25. So I get a force of 280 newtons. Okay. Let's see, where are we at time-wise? Oh, we're pretty much there. Okay, so when we come back, we will talk about the second part.